Hey, how's it going? So for this module, we'll be looking at arc length and sector area. These are the two formulas for arc length and sector area. Notice that they're both in radians. So if you're given a problem and it's in degrees, you need to convert it into radians. As a reminder of how to convert an angle from degrees to radians, you would take the angle that's in degrees and multiply it by pi over 180. And then once you simplify, that's going to be your same angle, but now it's going to be in radians. The formulas that they're given to you are both in radians. There's no degree sector area. There's no degree arc length formula on your formula sheet. So in regards to arc length and sector area, make sure that you're living in the world of radians. All right. So let's go ahead and look at our first example. Our first example, we're going to find the sector area of DC. So DC is this red arc right here. All right. So for the sector area, it's 1/2 times r squared times theta. Theta here is 2 pi over 3. 1/2, of course, and then r squared, our radius is 8, because this is given. Let's go ahead and plug it in and evaluate. For a problem like this, you need to be able to get to this step by yourself without a calculator. All right. So that's just something to make sure we keep in the back of our mind. So now let's go ahead and look at the arc length of the same sector of DC. We'll go ahead and just plug in the radius and the angle. And once again, we'll simplify and we'll get 16 pi over 3. Now, what if we want to find the sector area of arc length of the other arc? So when they give you, say, DC, they're saying the shortest route between point B and point C on the arc or on the circle. All right. If they're talking about the larger one, it'll be DBC. All right. So if it's just two letters, they're assuming that you're talking about the minor arc, the shortest route. All right. So then here is DBC. So the sector area of DBC. So we know the radius still, but we don't know the angle. So a full circle is 2 pi radians. All right. Something to just kind of throw out there, how to live in the world of radians, as I would say. 2 pi over 3 radians, right, for this angle here. So that means the full circle is going to be 6 pi over 3 radians. So whatever your denominator is, if it's in the form of pi, whatever your denominator is, multiply it by 2, and that's what the numerator is for the full circle. So if it's 2 pi over 3 radians for this angle, that means the full circle is going to be 6 pi over 3 radians. Because remember, 6 pi over 3 is going to be 2 pi. All right. So if the denominator was 5, it'll be 10 pi over 5 will be the full circle. All right. So if I know the full circle is 6 pi over 3, and this angle is 2 pi over 3, I would just take 6 pi over 3 minus 2 pi over 3 and get 4 pi over 3. And then I just plug it on in and evaluate, simplify, and I should get 128 pi over 3. Same thing for the length of the arc. So if I was looking for the arc length of DBC, I still have to take 6 pi over 3, subtract 2 pi over 3, and get that angle. All right, that's a very common thing that you might have to evaluate for with problems like this. You simplify and you get 32 pi over 3. All right, so what about a problem that looks like this? We're still given the radius of 3, and now you're given the arc length right here, which is 2.70. All right, so we have the arc length, but we do not know what this angle is yet. Let's go ahead and find that angle first. All right, so what do we know? We have a formula for arc length, so go ahead and write out that formula for arc length. All right, the arc length is equal to the radius times theta. I don't know what theta is, but I know what the radius is, and I know what the arc length is. So that's enough information to divide by 3 on both sides, and we will get the angle measurement, which is 0.9 radians. All right. So while the angle is 0.9 radians, it's not in the form of pi. That's perfectly fine. So that means the rest of your answers, you would kind of put it as a decimal as well. All right. But as a reminder, if we looked at the previous problem, we treated the circle as 2 pi radians, which it is. But because it's but it was in the form of pi. But because it's a decimal, instead of saying 2 pi radians, we're going to say 6.28 radians, which is 2 pi radians. But because it's in decimal form, we have to treat it as such. All right. So if this angle is 0.9 radians, I would take 6.28 and subtract it by 0.9 to get this angle here, which we'll use later on. So first, let's go ahead and find the sector area of NJP. All right. So we're looking for this sector area here. The sector area formula is 1/2 times the radius squared times theta. We know what all that is now. We know what the radius and we know what theta is. So we just go ahead and evaluate. 3 squared is 9. And then once you multiply everything together, you get 8.1 times 1/2, which is 4.05. So that's the area of this sector. Notice how you were originally given the radius and the arc length here, and you had enough information to go back and find the sector area. So now we're going to be looking at the major arc. So we're going to be looking at the arc length of NVP. We're looking at the other side. So if I know that this angle is 0.9 radians and the full circle is 2 pi radians, which is also 6.28 radians, I know what's left is 6.28 minus 0.9, which gives us 5.38. And then when I multiply that by 3, which is our radius, that tells us what the arc length is, which means the rest of this arc that's not in red here should be 16.14. So now let's go ahead and find the sector area of the remaining arc. So then now we know that that's going to be 5.38 in regards to the angle measure over here. We also know that the area of the sector is 1/2 times the radius squared times theta. So let's go ahead and just plug in what we know. We know 1/2 times the radius, which is 3. And we know the theta, which is 5.38, because we took 6.28 minus this angle here. That gives us the remaining arc here. All right. So then now we have enough. So now we just go ahead and evaluate. And once you do that, you get 24.21. All right. So 24.21 gives us the area of the sector of NVP here. All right. Notice, go back to the original, what was given, the original problem, what was given. You were given the arc length of this minor sector here and the radius. And that was enough information to find the sector area of the major arc. All right. It's not going to always be given to you where step by step where we gradually progress like we did in here. But understand that as long as you're given that information, whatever information they give you, that's probably enough information to get to your answer. So you got to think about what is being given. All right. Now, what can I find with the information that's given? And then use that information to find out what you need. So let's go ahead and look at our next example. The area of sector JKL, which is this area over here, is 56. The angle of JKL, which is right here, is 2.8. So it's in decimal, so we know that we're going to be treating the full circle as 6.28 radians, which is equivalent to 2 pi, which is also equivalent to 360 degrees. But we're going to be dealing in radians because our formulas are in radians. And as a reminder, if it was written in degrees, you would multiply your degrees by pi over 180 to convert it into radians. So we know we have area of a sector. We got a formula for that. Plug it in. All right, so it'll be 56 equals 1/2 times r squared, which I don't know what that r is yet, times theta. So once we plug that in, it should look like this. All right, so then now we got to solve for r. So you can multiply 2 to both sides and divide by 2.8 to get r squared by itself. And then you would take the square root of both sides to get r by itself. All right, I divided by 2.8 first on both sides and got 20. Multiplied by 2 next and got 40. Took the square root of 40 and got 6.325 or 2 square roots of 10. All right, either way is fine. Remember, if they want exact values, it would be 2 square root of 10 as your radius. And you still can find all the answers with that exact value still. Let's go ahead and move forward. I'm going to treat it as 6.325 though. All right. If I want to find the arc length of JL, so the arc length, we're going up to this formula, L equals radius times theta. The radius is, what do we find the radius is? 6.325 times theta. And we know this angle here is 2.8. So we just plug it in and evaluate and we get 17.71. So now let's look at the next one. Let's find the sector area of JML. Okay, so now we're looking at the major arc over here. JML here. So the sector area is 1/2 times the radius squared. We know that's 6.325 squared for this portion of the formula times theta. If I know that this is 2.8, I know the angle on the other side has to be 6.28 minus 2.8. All right, because 6.28 is how many radians you have in a full circle. So once I do that, I should get 3.48. Now I can just simply evaluate and get the area of 69.610. So that's the sector area of JML. So now the last piece for this problem, let's find the arc length of JML, so the major arc. Go back to the formula, radius times theta. We know the radius is 6.325 and we know theta is 6.28 minus 2.8, which we already know, which is 3.48, which when you evaluate should give you 22.011 as the arc length from J, M all the way to L. So now, what is the area of the shaded region? Like, how do you find a problem out like this? Like, how do you find this shaded region here? So this is a very popular problem that has been seen historically. So then the way you would do that is the area of the shaded region is equal to the area of the sector minus the area of that triangle. So let's get started. Let's start by finding the area of the sector. Remember, the sector area formula is 1/2 times radius squared times theta. So 1/2 times radius squared times theta. We know that the radius is 8.2, and we know that the theta is 1.5. So go ahead and plug those in and evaluate. So that means the area of that sector here is 50.430. But that's more than what we need for the shaded region. So now we have to find the area of this triangle somehow and subtract that. We got to pull everything that we've been doing historically in. All right, think about it. If this is a triangle and your angle here is 1.5 radians, of course, this side length is 8.2. It's a radius, right? That 8.2 is the radius. So if this side length is 8.2, this side length has to be 8.2 as well. Now you have enough information to find the area of that triangle. All right, remember, the area of a triangle is 1/2 times A times B times sine C. Your sine C is 1.5. Your A and B are both 8.2 and 8.2. Just be careful. When you put this in your calculator, you got to make sure your calculator is back in radians because this 1.5 is radians here. All right, so long as it's back in radians, you could plug it back in just like this. And once you evaluate, you should get 33.536 as the area of this triangle here, of that triangle. And if we know the area of that triangle is 33.536 and the area of that sector is 50.430, you just subtract the two, and then that will give you the final answer of 16.894, which is the area of this shaded region here. All right. Now, what is the length of the chord though? Let's look at this triangle again. If I know that this side is 8.2 and this side is 8.2 and this angle is 1.5 radians, and I want to know what the length of this chord is right here, that's just the third side of a triangle. You got two sides with an included angle. You can use law of cosines here. So law of cosine, looking for that missing side, plug in your A and B, which are both 8.2. And then this angle C, which is your included angle, is 1.5. And then you evaluate, take the square root of both sides, and you get 11.179, which means that is the length of that chord. And just like that, it's time to practice. If you have questions or concerns, feel free to let me know.